The last topic we will discuss today is principal component analysis, and this will be useful for multiple courses in this lecture in the future. So remember the Fourier transform. It converted an image into a domain, basically a frequency domain. And we could actually look at the magnitude here or the phase. So it actually created another representation of the image. Now we applied it to basically the entire image, but you can imagine applying it to different parts of the image. And this is much like actually extracting features. You create a new representation of the image or its parts. And these features, like the ones that we've seen just now, can actually be used to basically recognize things, track things, detect things. Now, Fourier transform is an all-applicable generic unitary transform. And obviously, it may not extract best possible features. It only looks at the sinusoidals. But the idea is, can we have transformations specific to certain image types that can be used for such purposes? One example is principal component analysis. Now, the motivation is actually quite simple. So we want to create an image-independent, so the image-independent transforms are suboptimal for extracting useful descriptors or representations. Instead, we want image-dependent transformations that may yield more useful representation of the images. Useful in terms of detection tasks, recognition tasks, restoration tasks. And one such transformation is called principal component analysis, or shortly PCA, which is also known as Carhun and Löwe transform, KLT. PCA extracts statistics from images for a customized orthogonal basis with uncorrelated weights. Here, we will talk about the uncorrelated part. But customization refers to having a basis set that is specific to a given set of images, instead of using generic bases such as those used in Fourier transform, like the complex exponentials. The central idea in PCA is to reduce the dimensionality of data consisting of many interrelated variables, while retaining as much as possible of the variation. And this we achieve by transforming it to a new coordinate system, which we'll call the principal coordinates, or principal components, which are ordered so that the very first few principal components will basically retain most of the variation seen in the images. And this representation, as I said, will actually be, or if we represent the image under these new variables, they will actually be useful for various tasks. First, let's look at the entire concept in very simple two dimensions. By correlated variables, what we mean is we have an observation, for example, like the one given here in the x1 and the x2 coordinates. Now, you can actually imagine that each of these samples is an image, but let's look at here just in two dimensions. So observations like this show that there is a high correlation between the variables x1 and x2. These, for example, can be the grade level at neighboring pixels, which are supposed to be similar, or the length and the weight of growing children. We know that, for example, as the length increases, the weight also increases, so there is a high correlation. Which also means that x1 has a lot of information about x2. So looking at these plots, we can actually represent both variables with only one. And this new variable would be a much more compact representation and would basically has information on both of the previous ones. For example, this new representation can tell us the age of the children. So the basic idea in PCA is to achieve decorrelation through rotation. So using the correlation structure that we see in the image, in the x1 and x2, for instance, we will rotate the coordinates and obtain the new coordinate system z1 and z2, such as to maximize the variation in the first component and minimize the variation in the second component. So we see that if I actually rotate the image, rotate the coordinate system, now the variation in the z1 component is very large. By variation, what I mean is a dispersion of the samples on that axis. While the dispersion of the samples on the z2 axis is very small. Then I can actually potentially drop the second component and only represent the data with Z1. Now, this is a 2D simple example, and we've seen through rotation, but this also applies in higher dimensions, as we'll see in a second. The principle behind is exactly the same as unitary transform. We apply rotations in high dimensional spaces to achieve certain tasks. In this case, decorrelation and obtaining few coordinates with high dispersion and the remaining coordinates showing no dispersion. We will obviously actually work only around the mean of the data points. Thus, we will actually demean the data points and really create a coordinate system whose origin will sit right at the center of the samples. Thus, we're actually applying a rotation about the mean of the samples, or if you like, the mean of the distribution. And this is really, in essence, fitting an ellipse to the data. Ellipse has two different axes, V1 and V2, and the size of the ellipse changes as well. So we really want to fit an ellipse to this data set, centered at the center of the data. And the analogy extends to hyperellipsoids in higher dimensions, where visual inspection will not be possible. One thing to note is, through rotation, we keep something constant in the data. Through rotation, the sum of the variances does not change. We can actually prove quite easily that if I look at the variances of the original coordinates, so sigma I square here corresponds to the variance of the data samples that I see in the xi direction, and sigma tilde I square corresponds to the variance in the zi direction. The sum of these variances do not change. So the energy of the system remains constant. I simply redistribute the energy to different coordinates. And this invariance stems from the fact that the rotation does not change the center of gravity of data samples, and rotation does not change distance between different sample points. So in the end, it satisfies the Parseval's equation. So the energy remains the same. So the idea about the PCA is we want to redistribute the energy. So redistribute sigmas into new sigmas, such that if I plot these sigmas, very few of them will be very high, and the rest will be close to zero. That's the goal. Now, in the 2D case, we could actually achieve this simply by visual inspection and finding the correct rotation, but this will not be possible in the high dimensions, so we need some level of abstraction. And the required statistics is what's called the covariance matrix. So in PCA, there's really an underlying Gaussianity assumption. The intuition is I want to fit an hyperellipsoid to the cluster of data, and the subsequent principal components will correspond to the axes of this ellipsoid, starting from the longest axis going to the shortest one. So the method can be described as follows. Suppose X is a vector of D random variables. So we can imagine that if X is an image, then D can be the number of pixels. The first step is you look for a linear combination of X. So a vector C1 that has the same dimension as X, such that if I project X onto C1, the result will have the maximum variance. Okay, so I want the C1 where the data samples has the largest dispersion. Once I find C1, and that I can find, in the second step, I now try to find a C2 that is orthogonal to C1 and still achieves the maximum variance. And in the third step, I repeat. I find a C3 that achieves the maximum variance while being orthogonal to C1 and C2 together, and so on. So mathematically what it corresponds. So we will assume that all samples are d-meaned, meaning that if I have n data samples xn, the mean of them will be 0. Okay? So I extract the mean separately. Once I'm given that, I simply compute the variance of the data samples in the C1 direction. So I project all data samples to C1, and I compute the empirical variance on that point. So computing the empirical variance simply corresponds to multiplying the projected values with themselves. So I write it in the vector notation. This will become clear why in a second. So I want to maximize this empirical variance of the n samples such that C1 is an orthonormal vector. So C1.C1 is actually 1. Now, if I actually do the maximization, let's keep the constraint at the side for a second. I can actually write this simply as, transpose will basically change this such that this summand will basically C1 transpose times xn transpose times C1. Since C1 does not depend on n, it can actually get out of the summation. So then C1 transpose times sum times C1. And notice that this form here is actually the empirical covariance matrix of the samples, which I can write simply as capital C. So this maximization boils actually to maximizing this form, so C1 times empirical covariance matrix times C1, such that C1 is a unit vector. Now, using Lagrange multipliers, I can solve this constraint optimization problem. I simply now maximize C1 transpose empirical covariance matrix C1, and then minus the Lagrange multiplier lambda, and then my constraint, so that the vector is unit length. If I take a derivative with respect to C1 and set it to 0, this is the equation that I get. Now, this equation should actually look familiar. This is exactly the same equation that you would use to find the eigenvectors or eigenvalues of a matrix. More clearly writing it like this, I think it becomes clear. So thus, lambda must be an eigenvalue of the C, which is the sample covariance matrix. And C1 must be the corresponding eigenvector. But if C is a matrix, it has multiple dimensions, right? So which of the D eigenvectors? Which one are we talking about? So again, we can compute this quite easily. So assume that C1 is an eigenvector. So then C1 transpose C times C1 will basically be the same as C1 transpose times the eigenvalue times C1. If C1 is a unit length, this will correspond to lambda. So if I want to maximize this form, that basically means maximizing lambda. So since lambda is the eigenvalue, that basically means this lambda should be the largest eigenvalue of the sample covariance matrix. Therefore, C1 must be the eigenvector that corresponds to the largest eigenvalue. Okay? And notice that it's clear here, but to write explicitly, lambda here corresponds to also the variance of data in the C1 direction. Okay. Now we have our first principal component, and we also know the variance in the principal component direction. How about the second one? What we want is we want to maximize the C2, the same thing again, C2 transpose times the sample covariance matrix and C2 while being orthogonal to C1. Again, let's write in Lagrange multipliers. Now we have an additional Lagrange multiplier term telling that the C2 must be orthogonal to C1. Differentiation with respect to C2 and setting it to 0 gives me this equation here. Now, if I multiply this from the left-hand side by C1 transpose, I basically get this guy here. So C1 transpose C2 and this third guy. And if I now impose a condition that C2 must be orthogonal to C1, then I actually get the necessary value of the Lagrange multiplier eta, which should be 0. So therefore, the stable equation actually can be given as simply the eigenvector equation for C2. So just by looking at this equation, I notice that C2 now should also be an eigenvector of the sample covariance matrix capital C, and the lambda should be the corresponding second largest eigenvalue, since it should maximize this guy. How about the kth principal component? The same principle applies. So the kth principal component is simply the eigenvector corresponding to the kth largest eigenvalue. So given a certain set of data, I can now easily compute the principal component. I can easily do the principal component analysis and compute the principal component simply by first computing the empirical covariance matrix of my samples, and then apply the eigenvalue decomposition on the matrix, and the resulting eigenvectors will be the principal components. And then I simply order the components based on the magnitude of the eigenvalues, and note that eigenvalues will correspond to the amount of variance in each principal component direction. That's it. Now you can ask, are these new variables decorrelated statistically? Now in the 2D case, the decorrelation was very obvious. Like through rotation, we could actually see that Z2 and Z1 had no longer any information about each other. In higher dimension does this hold? Now we can estimate the covariance using our sample again. So the new variables, I will call them as Zi and Zj. So the covariance between these variables can be computed, or sample covariance between these variables can be computed like this. Now, placing Zi and Zj with the principal components and the data samples, I see that this becomes Ci projected, xn projected to Ci times xn projected to Cj. Now, placing everything on each other, I notice that this can be actually written as Ci times the sample covariance matrix times Cj. And note that Cj and Ci are eigenvectors. So actually, it's equivalent to this or this guy. Well, lambda j and lambda I are both scalars, and I know that Ci and Cj are eigenvectors, therefore they're orthogonal. So this product is 0. Therefore, the covariance between the new variables are 0. So they are decorrelated. Now, C is the sample covariance matrix, and there's a trade-off here, which is if the number of independent samples is higher than the number of dimensions, meaning that if n is larger than d, then C will be full rank, it's a positive semi-definite matrix, and it will admit d real non-negative eigenvalues and the corresponding eigenvectors PCs. So that's actually quite nice. In this case, we can actually use the eigendecomposition form. So the sample covariance matrix will be given as U, the lambda, and U transpose, where U will hold the eigenvectors in its columns. And lambda is a diagonal matrix of eigenvalues. So in its diagonals, it will have all the eigenvalues. And notice that in this case, it's quite easy that the principal component analysis is a rotation, because the transformation matrix U transpose U is an identity. So I actually still do a rotation in the high dimensions. So some notes. So PCA collects maximum variance in the subsequent uncorrelated components. And in a sense, any sample can be represented using the principal components and the corresponding variables, and vice versa. So I can actually compute the new variables, the new representation of my data, simply by projecting my data samples onto my principal components. Or I can represent any data samples by simply projecting the new variables onto the principal components, but this time onto the principal components, while the first one was the transpose of the principal components. Now, one point we didn't actually talk about much was, we talked about the case where we have number of samples was higher than number of dimensions. Whenever you talk about the images, this will not be possible. Actually, the number of samples will almost always be less than the number of dimensions. In this case, instead of using the eigendecomposition of a matrix given as here, as this guy, you would actually compute the singular value decomposition. And singular values, or the singular vectors, are actually will be the same as the principal components. One important point here is representation with fewer principal components. So in this data representation form, you see that any data point can be represented in terms of new variables. You can imagine that I can actually drop columns here and the representation of the variables here. So I can actually reconstruct a data sample using fewer number of new variables. In that case, what happens? Well, obviously, I will lose some information. But how much information I lose will really depend on the how much variance is captured with those fewer number of components. Specifically, if my data is very strongly correlated, then the first PCs will contain most of the variance in the data. So if I actually plot my eigenvalues with respect to the principal component index, a very strongly correlated data will show such a curve, which basically means that most of the variance in the data is actually captured by a very few principal components. So I can actually represent the samples only using a very few number of components here. As opposed to this, if I actually look at a weakly correlated data, then the principal components will have such a curve. So actually all principal components will have high values, meaning that in order to faithfully represent the data, I need a lot more principal components. So there are many applications of principal component analysis, and you will see some of them in the texture analysis course. Next week, you will see some of them later on in the recognition course. But let's here talk about one of the very first examples in computer vision, the eigenfaces for recognition that was proposed by Turk and Pentland in Journal of Cognitive Neuroscience in 1991. So it's a very primitive model, retrospectively looking, but has all the ingredients. And it's quite nice to see. So what they did in the study is actually they took a training set of only 16 images, so only these images. And they used these images to compute principal components using singular value decomposition, as we mentioned before. Now, these images are training images because I use them actually to compute the principal components. And each of these images is of size 128 by 128. Now, first, they demean the image. So this is the mean face of these images. And they take it out from all these samples before computing the principal components. And here they show 7 principal components that they were able to compute based on the data. Now, with only using 7 principal components, they were able to reconstruct faces of new individuals quite well, actually. So here the image is 128 by 28, and they reconstructed only with 7 variables. So they actually reduce the number of variables from somewhere around 16,000 to only 7. And you see the reconstruction is not very bad. So it's quite interesting. It's really a huge compression of information that you need to represent the data sample. Notably, this transformation would not apply to any type of image. It's, again, image type specific. So if I actually try to reconstruct the image of a flower, then they show that it does not work. I'm not able to reconstruct this image. A fun application that they play with is actually restoration. Let's assume that I have this image, but some part of the image is gone. I can actually take this image and project it into the new variable z, and then reconstruct the image using the new variables. And I see that when I reconstruct it, actually the PCA components are able to recover the information in this missing part. So they're actually correct for the occlusion. That's quite nice. And you will see more examples throughout the course, as I said, in texture analysis and object recognition.